My name is Dr. Nicholas Theodore, Professor of Neurosurgery and Biomedical Engineering at Johns Hopkins. I would like to welcome you all today to the HEPIUS Lab. The HEPIUS Lab is a unique environment bringing together surgeons and engineers to solve very complicated problems. My area of interest is spinal cord injury, and for the past 20 years, realized that we have brought to bear no significant treatments for patients who have suffered this devastating problem. In this lab, we are working on a daily basis to bring ultrasound and other techniques together to treat these patients. Let's go inside and take a look.
Hi, my name is Amir Manbachi. I'm an assistant professor of neurosurgery and biomedical engineering at Johns Hopkins Medicine, as well as the co-director and co-founder of the HEPIUS Innovation Center. Today, I'm excited to talk to you about some of the exciting and futuristic things we do in this research center. As you heard from Dr. Theodore, spinal cord injury is a significant unmet need, and we would like to help. We would like to help the patient with spinal cord injury. This is not about us. The last thing we think about is about ourselves. This is about the patient with spinal cord injury. And we're coming from different aspects, different backgrounds. We're thankful that we have assembled a world-class team from around the nation with different backgrounds so that hopefully we can help that patient with spinal cord injury. One thing this center is all about, particularly, is the marriage of two fields, sound and spine. So as you can see here, people from all around the world have come together as part of this HEPIUS program funded by DARPA, Defense Advanced Research Program Agency, so that they can tackle the problem of spinal cord injury using ultrasound. So in this lab, in the HEPIUS Innovation Lab, we are all about the marriage of sound and spine. We think on a daily and hourly basis about the different applications of ultrasound. Ultrasound can do imaging, ultrasound can do flow sensing, it can do neuromodulation, tumor ablation remotely, it can do drug delivery and many different applications. On an hourly basis, what we think about all day long, day in and day out, is what can we do with sound that can help the patient with spinal cord injury. And we hope this initiative leads to some sort of help that's meaningful to our patients. Thank you, and I look forward to tour you around the lab today. As discussed, this is not about us. We are here because of the patient. So we start with patient in mind, and we end it with patients. We always talk with clinicians, we get input from them, and this table is the first table that you see in the lab as you walk in. So the first table is our sonography table. We look into various things, try to image various things, and we try to understand under what parameters are we able to do the job that we want the ultrasound to do. With that said, I would like to invite Dr. Fariba Ağabeyoglu, one of our postdoctoral scholars in the lab, to talk about this table and the science she does in the lab.
Thank you, Dr. Manbachi, for the introduction. We use ultrasound as a diagnostic imaging technique as well as a therapeutic tools. We use high-frequency speed waves in order to see body organs, monitor blood flow, see abnormalities, and observe the improvement of treatments. In this table, you can see devices and tools we use for validation and evaluation of details and specifications for our research goal and purposes. We have a multi-purpose phantom, general phantom, a Doppler phantom, and a string phantom. This is a commercial imaging ultrasound system, as well as a peripheral Doppler phantom. I'm going to show you how, using the Doppler imaging modality, we can see a channel which represents blood vessels and flow of the blood inside this. We use this information in our next medical device design and fabrication. Thank you.
So far, you heard from Dr. Fariba Ağabeyoglu about clinical ultrasound scanners and how she uses that in collaboration with radiology and sonographers to look at anatomical structures, static anatomical structures that you heard about, multi-tissue or general purpose phantom. Now moving from clinical scanners and anatomical static images, now we want to talk about research ultrasound platforms and how ultrasound can be used to monitor flow. So here I'd like to introduce you to Haley Abramson. She's one of our PhD students. In fact, my first PhD student in biomedical engineering. And she can talk to you about what she does for her PhD thesis with me and Dr. Theodore. So without further ado, Haley.
Thanks, Amir. I have a background in software engineering, so I'm hoping to be able to translate the data we collect from the ultrasound devices that we're making in the lab and write an algorithm that uses these data and translates them into one number that clinicians can interpret. So Fariba just did a great job showing us the clinical ultrasound machines. And what I have here is a research ultrasound machine called the Ultrasonic system. I can use the code to manipulate all the ways that we can collect data, whether it's through a standard 2D image or through spectral Doppler. And I can take these and do whatever sort of analyses I need to do to understand and calculate different values that may be important to clinicians. So for example, here I have a cardiac Doppler phantom that sends fake blood through these tubes in such a way that mimics the heartbeat. Then I can calculate the velocity that the blood is flowing through the tubes and translate this into cardiac output if that's what we want to monitor. This translates directly to our music implant because we want to monitor blood perfusion at the injury site for over time in patients. And in this way, we can take all of the data that we're getting, put it into one number, monitor the patients for a long time, and establish our goal. Thank you for listening.
So far you heard how a problem stemmed from the neurosurgical world has resulted in a whole world-class team around the nation coming together from radiology, sonography, and engineers from various backgrounds, biomedical engineers, electrical engineers, and mechanical engineers to solve that problem. So we talked about the table that was all about sonography and clinical ultrasound. So moving on from that, as engineers, we like to see experiments in a controlled fashion. We want to tackle problems one parameter at a time. So to that end, we're moving from the clinical sonography table to an engineering/physics table for our ultrasound. In parallel, you also heard about clinical and research ultrasound scanners that are able to allow us to do imaging and flow sensing. Another application of ultrasound is therapeutic ultrasound. We are able to do neuromodulation and ablation of tumors remotely using ultrasound. So with those two things in mind, the engineering and physics studies of ultrasound and therapeutic ultrasound, it's in that spirit that I'd like to introduce Dr. Eli Curry, one of our postdoctoral scholars in this HEPIUS lab. Without further ado, Eli.
Thank you, Dr. Manbachi. At this table, we're focusing on trying to understand what focused ultrasound does in three-dimensional space. So to start, we're working with a cutting-edge focused ultrasound transducer system, the NeuroFUS system, and this allows us to generate a precise targeted region of focused ultrasound, which will allow us to stimulate a very specific region of the spinal cord. This will help guide essentially the design of our music implant for the ultimate DARPA project. Now, in order to understand what's happening at the focal point of the NeuroFUS probe or the music implant, we can use two different approaches. One approach is using a thermochromic sheet, which allows us to visualize the heat generated at the focal point of the focused ultrasound array. Another approach is using this benchtop testing tank. Now this allows us to use a microphone to three-dimensionally map out the acoustic sound pressure generated from either the NeuroFUS system or the music implant, and helps us ensure that we're precisely targeting a very controlled region of the spinal cord to ensure the music implant helps rehabilitate spinal cord injury patients successfully. Thank you.
In the engineering world, we have different terms such as R&D and V&V. R&D standing for research and development, V&V standing for verification and validation. So if you go into industry trying to make a medical device, these are the common terms. So far we talked about R&D, research and development, or we talked about the design lab, and once you design, you need to develop something or fabricate something. So as engineers, we can talk a subject to death, but nothing beats actually having a prototype to be able to show and look like prototype, or even better, if you have a prototype that actually functions. To that end, we have we have created a development lab, much like a mini fabrication shop for our own HEPIUS Innovation Center. And as part of this lab, we are lucky to have Richard Mejia and Eleanor O'Callaghan helping us out with the development activities. So without further ado, Eleanor, floor is yours.
One of the highlights of the lab is the ability to do metal 3D printing in-house. This advanced additive manufacturing process gives us the ability to design and create parts that would otherwise be too expensive or complicated to create using traditional manufacturing methods. Being able to 3D print with materials like stainless steel is critical to making long-lasting fixtures and devices that can be safe in and withstand the medical environment. Behind our metal 3D printer here, we've got two plastic SLA 3D printers. These 3D printers work with a variety of different engineering-grade materials and can print with extremely high resolution, going down to 25 micron layer thicknesses. Eventually, those printers will also be running with biocompatible materials for use in implants. Over on the other end of the lab, we have our laser cutter, which we can use to cut sheet material quickly and make fixtures and enclosures that we can use to test and validate the devices that we're creating here. And finally, also over down by the laser cutter, we have our 3D scanner. This 3D scanner can allow us to quickly make models of the devices that we're making in the lab and compare them to what was designed, as well as make 3D scans of parts that would otherwise be too complicated to accurately model. This is our laser cutter, which is a really useful tool for rapid prototyping that can cut a variety of different materials of different thicknesses. Not only can it cut, but it can also etch and raster.
So far, you heard us talking about design, development, verification, and validation. This section is all about validation, specifically preclinical validation. So it's all about testing in a realistic setup. So what we're going to talk about here is a sim center or simulation center, or what we call it a mock operating room, that allows us the unique resources to be able to simulate what's happening in the real world. So for example, if we design, develop, and test something that matches our specifications in engineering, usually as inventors, we're guilty of thinking our inventions are the best out there. Usually it's not. The way for us to learn that and go back and iterate on our design is to test in-house, and that allows us to reiterate our design going forward. So Rasika Tombre is one of our master's students in biomedical engineering, Hopkins BME, her first year master, and she will be talking to us about how her master's thesis is forming in the simulation center.
Thank you, Dr. Manbachi. So I will be walking you through the surgical space that we have here at our Bayview space. And basically, surgeons look for devices that are sort of effective, user-friendly, biocompatible, and easy to use. So before we introduce this particular device into a clinical setting, we sort of do a validation testing here at this surgical space. If the device needs to be implanted, we can implant it. We can do a basic implantation and also image it using an ultrasound probe. So this sort of preclinical testing gives the surgeon sort of an assurance about how good the device is and also like a preview of its actual functioning. So this is what we do at our surgical space. Thank you.
On behalf of the entire HEPIUS team, I would like to thank everybody for their time today and joining us on our grand opening. I would particularly like to thank the Departments of Neurosurgery, Biomedical Engineering, and the School of Medicine for their support in this endeavor. It is vital that all entities work together to help solve these terrible problems.
Same here. I'd like to echo the thanks. We are very grateful for all the opportunity and all the support we got. Definitely setting up a lab during the pandemic wasn't easy, but it's because that all the support structures stepped up that we were able to build this lab and work on this amazing, exciting, and futuristic DARPA award. Unfortunately, because of pandemic, we weren't able to have everybody in the lab the way we wished to. However, if anybody's interested, we're all about collaboration. So we welcome you to get in touch with us, set up a tour. We're happy to do a one-on-one tour, and we look forward to hearing from you. Thank you.